Assalamualaikum warahmatullahi wabarakatuh, and good evening to everyone. Okay, my name is Noor Amirudin bin Azlan, and my matrix number is 208062. I'm from Group T. We present about partial differential equation. For the first, we divide into three topics. The first one is wave equation, which is presented by me, Amirudin. The second one is heat equation, will be presented by Haridz, Syahmi. And the last one is Laplace equation, which is will be presented by Farah, Zulaikha. Wave equations. Principle of wave equation. The wave equation is a second order partial differential equation that represents the propagation of oscillation at a fixed speed in some quantity. Okay, for that is 1 over v square 2 v square times delta y over delta t is equal to delta y delta x. Duration of wave equation. Here is shows a piece of string displaced by a small amount from equilibrium. The force acting in a small element of mass d, m is considered to contain in a small interval of dx. The horizontal force is nearly negligible when the displacement is minimal. Hence, the vertical force can be expressed as Fy equal to negative t prime sine theta 2 minus t sine theta 1 is equal to dm times a, and we will get mu dx delta y over delta t square, where mu is the mass density, mu equal to delta m over delta x of the string. Because of the horizontal force for small displacement is approximately 0, so that t cos theta 1 approximate t1 cos theta 2 approximate t. Therefore, we will get negative mu dx delta y over t approximate t prime sine theta 2 plus t sine theta 1 over t. From here, we will get t prime sine theta 2 over t prime cos theta 2 plus t sine theta 1 over t cos theta 1. And the solution is tangent theta 1 plus tangent theta 2. After the derivation from tangent theta 1 plus tangent theta 2, and the final equation comes as mu over t delta y over delta t is equal to delta y over delta x squared, where this equation satisfies the wave equation from here, which is the velocity v is equal to square root t over mu. Finally, the application of wave equation is usually used in damping. During damping phenomena, the amplitudes of the wave will be reduced due to air resistance and non-elastic processes in the string, and the motion will eventually fade out. This damping effect can be modeled by a term by deriving equation 2. Here is the equation 2. On the left-hand side of the equation. Hence, we will get mu delta y over delta t plus b delta y over delta t equal to t delta square y over delta x squared. And the parameter b must normally be determined by the physical experiments. That's all from me. Thank you.
Assalamualaikum and hello everyone. My name is Ahmad Syahmi bin Husairi. My matrix number is 207846. So now I will be explaining on the heat equation. The heat equation is to help us solve the heat equation which governs the temperature distribution of the object. So first and foremost, we need to analyze the problem and change it into mathematical terms. As you can see here, the temperature at any point x and any time t, the specific heat, mass density, and the heat flux q are all being represented in mathematical terms, in which it makes it easier to turn it into a differential equation, which makes it easier to understand the heat equation. So next, Fourier's law. Fourier's law is introduced by Joseph Fourier in 1822, where it is about thermal conductivity. So here you can see the Fourier's law states that where K naught and all that is the thermal conductivity of the material and measures the ability of a given material to conduct heat. So by using the Fourier's law, it helped us to develop the heat equation, which was already produced in a one dimension earlier. So here is the heat flow and derived equations of the heat equations. As you can see, that there's a heat equation for a non-uniform bar will be example, and the initial condition for the 2D and the 3D heat equation. All of these are derived from the Fourier's law, from the one dimension formula of the heat equation. So that is how the partial differential equation is applied in the heat equation, which is widely used in physics and thermodynamics and such. So that is all from me. I will be passing the next part of the presentation to my group mate. Thank you very much.
Assalamualaikum and a very good day. My name is Farah Zulaikha, Binti Jafrikhairi, matrix number 207785. So now I'll be presenting on the Laplace equation. Laplace equation is a second-order partial differential equation in mathematics and physics named after Pierre-Simon Laplace, who was the first to study its features. Laplace equation is expressed as delta U is equal to 0, where the Laplace operator delta is defined in Cartesian coordinates by the equation shown. The equation of Laplace is a linear scalar equation. It is the prototype of an elliptical partial differential equation, and it shares many qualitative aspects with more extended elliptical partial differential equation, or also known as PDEs. The Laplace equation therefore converts one scalar function into another. The non-homogeneous version of Laplace equation, called the Poisson equation, is stated as delta U is equal to f, where f is a given function. Potential theory is the general theory of Laplace equation solutions. The solutions of Laplace equation are the harmonic functions, which are significant in many disciplines of physics, including electrostatics, gravitation, as well as fluid dynamics. The Laplace and Poisson equation, as well as their generalization, can be found in many different contexts, which includes, first, potential theory, for example, in the Newtonian theory of gravity, electrostatics, heat flow, and potential flows in fluid mechanics. Second, Riemannian geometry, for example, the Laplace-Beltrami operator, and the last one, complex analysis, whereas the example can be found in the real and imaginary parts of an analytic function of a single complex variable R harmonic. The application of Laplace equation in two dimensions. Laplace equation in two dependent variables in rectangular coordinates has the form as shown in the equation below. The application of Laplace equation in electrostatics can be explained by summarizing the properties of electrostatic fields in which they satisfy the laws of electrostatics as shown. Therefore, E is equal to negative del V as the consequence of del times E is equal to 0. By implementing this relation, Gauss' law can be rewriting as the equation shown, from which it satisfies the Poisson equation, where the equation is known as Laplacian of V. That's all from our group. Thank you.